Hello everyone, welcome to my device. In this video, we will be looking at the basal electrical rhythm or BER in short. This will be the first video in the series of motility of GIT. So let's start. So starting from the top, we basically have two types of motilities, electrical motility and mechanical motility. In electrical motility, we have basal electrical rhythm. In mechanical motility, there can be two situations. These are the fed state and the fasting state. Now, in the fed state, again, there can be peristalsis and segmentation. In the fasting state, we have migratory motor complex. So, in the series, we are going to learn about all of these four, but in this video, we will be looking at the basal electrical rhythm only. So, let's start. So, what exactly is BER? So, basal electrical rhythm refers to the rhythmic, spontaneous, meaning these electrical rhythms are produced by themselves, depolarization and repolarization of the smooth muscle cells in the GIT. Basically, it is the resting membrane potential of the GI muscles. This will become much more clear in a few minutes from now. Now, the question is what produces these basal electrical rhythms? So, in the GIT, we have a few cells called the interstitial cells of Cajal. These cells are also called as the pacemakers of the GIT. Just as we have the pacemakers in the heart, the SA node, we also have pacemakers in the GIT called interstitial cells of Cajal, and it is very important to know about these cells. So these cells are located between the muscle layers. So in the GIT, we basically have four layers, and I've already made a whole video on this called Introduction to GIT. So I really recommend you go and check that out. Here we have this muscle layer. We have the longitudinal and circular muscle layers. So most of these cells are located between these muscle layers. Now what else? So it is in these cells that there are spontaneous fluctuations of the membrane voltage. So the spontaneous depolarization and repolarization happen in these cells. They are located from the mid part of the stomach to the anal canal. And an important one-liner, C-kit is the marker of these cells. Important to remember. Now finally, let's see this basal electrical rhythm in a graph. So in the graph, we will see voltage and time. So as the time passes, since there is spontaneous depolarization and repolarization happening in these cells, the potential is going to look something like this. And these electrical fluctuations are the BERs. The potential of these basal electrical rhythms vary anywhere from -60 to -40. These waves that are produced here are called the slow waves. It is very important to note that these slow waves are not the ones which cause the contraction in the GIT because these are not strong enough. Something different happens when these membrane potentials reach to -40. At -40, we get waves like these. These are called as spike waves, and these spike waves are the one which help in the contraction of the muscles. So just summarizing, slow waves are not responsible for producing muscle contraction, but the spike waves are. Also, more are the spike waves, more strong will be the contraction. So if there are only one or two spike waves, the contraction will be weak. But imagine if there are 5 or 6 spike waves, the contraction will be then very strong. Now, before moving forward, let's quickly brush up on our basic physiology. So, you know we have the parasympathetic system and the sympathetic system. The main neurotransmitter in the parasympathetic system is acetylcholine, and in the sympathetic is epinephrine and norepinephrine. The parasympathetic system is activated when the body is in a relaxed state, and sympathetic system is activated when the body is in fight or flight mode. In the parasympathetic system, the motility of the GIT is increased, but if the sympathetic system is activated, the motility is decreased. Also, the digestive enzymes and gastric acid secretion is increased by parasympathetic system activation and is reduced by the sympathetic system activation. Now, having all this in mind, let us look at this graph one more time. Here we will be comparing the membrane potential with the tension in three different scenarios. So in the first part, we will only look at the basal electrical rhythm. In the second part, we will see what changes will be made if there is cholinergic stimulation. In the third scenario, we'll see what will happen to the membrane potential and tension if there is adrenergic stimulation. So, basal electrical rhythm you already know, these are just slow waves. And you know that the slow waves are not responsible for producing any contraction in the GI muscles. So, can you tell me what is going to happen to the tension in the GIT? Since there is no contraction taking place, the tension will be very low. It will not increase. Now, what happens when there is cholinergic stimulation? So, imagine if acetylcholine is introduced, the basal electrical rhythm or the slow waves are going to go past the minus 40 threshold. If this happens, we will get to see a lot of spike waves. And you know that the spike waves are the one which help in the contraction of the GI muscle layer. So what is going to happen to the tension? The tension is going to rise after each series of spike potentials. You can compare the spike potentials at the top with the tension in the golden line. You can see that soon after the spike potentials, you are getting a rise in the tension, meaning contraction is taking place. Finally, what will happen if there is adrenergic stimulation? So you know that norepinephrine or epinephrine inhibit the motility of the GIT. So obviously, the slow waves will not be able to reach the threshold, and so we are not going to get any spike waves. If there are no spike waves, so again, there will be no contraction. There will be only relaxation of the muscle layer, and so the tension is again going to decrease. I hope this is clear till now. Now, these basal electrical rhythms are different in different parts of the GIT. So, in the stomach, the basal electrical rhythm is only 4 per minute. So, those waves that you saw, only 4 waves per minute are going to be seen in the stomach. In duodenum, we have 12 per minute, jejunum 11 to 12 per minute, lesser than duodenum. In ileum, we have 8 per minute, cecum 2 per minute, and finally sigmoid colon 6 per minute. Now, two important questions that they can ask. Maximum basal electrical rhythm is seen in the duodenum, which is 12 per minute, while minimum is seen in the cecum. Now, just to make sure we understood everything, let us practice a few questions here. Which cells are primarily responsible for the generation of basal electrical rhythm in the GIT? So I think everyone can answer this question. The correct option here is option C, or interstitial cells of Cajal. Next question. The basal electrical rhythm frequency is highest in which part of the GIT? Stomach, duodenum, jejunum, or ileum? So we have just seen this. The correct option here is option B, or duodenum. This is actually a previous year question. Graph of which part of the GIT is being represented here? Now, this question is a little tricky but also very interesting. So, this is almost the same graph as we saw previously, but there is one small change. Here, they also have given the time duration of one small wave or basal electrical rhythm. So, here you can see that one BER is of 10 seconds. What does this mean? This means that one peak is occurring every 10 seconds, which means there will be 6 peaks in 60 seconds or in 1 minute. So if the PER is 6 per minute, you can go back and have a look at the table that we made. There we wrote that the BER, which is 6 per minute, is seen in the sigmoid colon. So here the correct answer is sigmoid colon. That's it for this video. If you have any doubts, feel free to message me on Instagram or leave them in the comments. I'll see you in the next video. Thank you.